Hi there, myself Madhav Jha. I welcome you to CodeChef and let's have a look at this question.
The problem is LIS and LDS. We are given a frequency array f of size n, and the original array A will be nothing but sum of all the elements in our array f. Now it is called good if it contains the integer x exactly f of x times. That is, our frequency array matches with our array A. If that is the case, we'll call it a good array. Now the score of our array A is defined as the minimum of LIS of A and LDS of A, where LIS denotes the longest strictly increasing subsequence of A, whereas LDS denotes the longest decreasing subsequence of A. And remember, these have to be strictly increasing and decreasing. Overall good arrays, we need to find the maximum possible score. So for the input format, we have t test cases, and each test case will contain two lines. The first line will contain the integer n, that is size of our frequency array f. The second line will contain n integers f1, f2 till fn. As for the output, we simply have to output on a new line the maximum score of a good array. As for the constraints, number of test cases will go from 1 to 10 raised to 4. Length of our array f will go from 1 to 2 raised 2 into 10 raised to 5, and the value of frequency array fi will go from 1 to n. Let's see how we can approach the solution. After that, we'll look at the sample examples. So we have our frequency array something like this. Let's take some values. We have 1, 2, and let's say we again have 1. What this means is the original array A will have only one occurrence of A, will have two occurrence of 2, and again only one occurrence of 3. Out of this, we will rearrange this and find out what is the longest increasing subsequence and what is the longest decreasing subsequence. And out of this, whichever is the minimum will be our score. So since we have to find out minimum among these two, we need to make sure that they are as close to each other as possible. We do want to maximize it, but we want to keep it as close as possible so that the minimum we can maximize. So let's take this example. What would happen if the value of our frequency is greater than or equal to 2? Since we know that both longest increasing and longest decreasing has to be strictly. So the maximum answer that we can get for longest increasing or decreasing can be n. That's it. We cannot have any more elements, because if we have n elements and we sort them in the increasing order, that will be the maximum length of LIS. If we put them in the decreasing order, that will be the maximum of LDS. And since the frequency is greater than or equal to 2, what we can do is we can use the one pair of each number for our LIS, and then we can use one pair for LDS. This is the base case. But what would happen if f of I is equal to 1? Now, if this is the case, let's say we have a count of C1s. This is something x, right? This is all the numbers that have a single digit frequency, that is 1. Now, in this case, we can use one element that can be common between both LIS and LDS. But we cannot do it with two numbers, because let's say if you have A and B, since these are strictly increasing or strictly decreasing, if A is greater than B and we are thinking in ascending order, we'll have to put it as AB. If it's decreasing, we'll have to put it as AB. If it's increasing, we'll have to put it as BA. So if two numbers are there which only have a single digit frequency, we cannot share them between both increasing and decreasing. But if there's a single number, we can do that. So for now, we have count of 2, that is any number that has a frequency greater than or equal to 2, plus we can take one more number from our C1, that is the elements that have a single count frequency. Now other than that, all the other numbers, right, let's say C1 minus 1, these are all the other numbers that have a single frequency. We can share them in longest increasing and longest decreasing, but we need to make sure that both of their length are very similar, because we are going to take minimum at the end. So what we can do is we can simply divide it by 2 and give half of them to increasing and half of them to decreasing, and with this we'll get our answer. The base will be all the numbers that have frequency greater than or equal to 2. Then we can share one element, that is the number that has a single frequency, we can share them between longest increasing and longest decreasing. And for rest of the numbers that only appear once, we can share half of them to longest increasing and half of them to longest decreasing. This we will take as the floor value, right? We can simplify this and make it into something like this. It will be nothing but C1 plus 1 divided by 2, but this will be the ceiling value. And this will be our solution. Let's see how we can implement the solution in C++. So for each test case, we'll call the function solve, and solve will take the input of n. Then for all the frequencies, we'll keep count of how many frequencies are greater than 1 and how many are equal to 1. For all those that are greater than 1, that will make our base, that is C2, and as we have seen the formula, for the elements that only appear once, we'll add 1 divided by 2, take its value, and we'll get the answer. And as you can see, I have AC in my C++ implementation. Let's see how we can implement this in Python. Again, for each test case, we call the function solve, take the input of n, then our frequency array f, then we calculate the count of C1 and C2. C1 being all the elements that appear only once and has a frequency of 1. C2 are all the elements that have frequency greater than equal to 2. And as we have seen, the formula linear approach, we put it in and get the answer. And as you can see, I have AC in Python implementation as well. So I hope you understood the problem, the approach, and how we can implement the solution in both C++ and Python. Have a very good day, and I'll see you in the next video.